first of all, notation-wise, when we're writing a vector, we typically use lowercase letters, and when we're writing a matrix, we typically use capitalized letters or uppercase letters. So some of the terms that came up today, the identity matrix. And sorry, that green's not showing up very well. I'll try to use red and orange more today. So the identity matrix, we denote with an I for identity, and then we give it a subscript that's going to tell us how large that identity matrix is. So if I put a subscript of 2, then the identity matrix for I2 looks like 1, 1 on the primary diagonal and zeros everywhere else. If I write an I with a subscript of 3, that matrix is going to look like 1, 1, 1 on that primary diagonal and zeros everywhere else. If I went to I4, I'll do just one more, I promise. If I go to I4, that means I'll have 1, 1, 1, 1, and zeros everywhere else. Okay. You might hear it referred to as the identity matrix or just see this notation of an I with a subscript. Now, each of these matrices has a particular size, and when we talk about the size of a matrix, we refer to that as the dimension. So this has a dimension of 2 by 2, that's how we read that. This has a dimension of 3 by 3, and this one has a dimension of 4 by 4. One of the things to know about matrices, all of the notation around matrices and the properties around matrices and sort of what we're doing with matrices all follow this pattern of rows before columns. So that first number tells me the number of rows, and the second number tells me the number of columns. Now, there are a lot of places where talking about rows or columns could be interchangeable. Specifically with a matrix, rows mean horizontal and columns mean vertical. So if I had a matrix with a dimension of 2 by 3, that matrix would have 2 rows and 3 columns. So maybe I would have something like 1, 2, -1, 4, 0, 3. So that has 2 rows and 3 columns. When I was first taking linear algebra, my teacher said, just remember all matrices are Roman Catholic. So remember that R comes before C. Our rows come before columns. Next vocabulary thing for matrices that I want to bring up. So a couple other things that came up in class today. A square matrix is any matrix where the number of rows equals the number of columns. So a square matrix could be a 2 by 2 or a 3 by 3 or generically an n by n. But a square matrix means that the number of rows equals the number of columns. Now there's a really particular kind of square matrix that came up today, and that's a symmetric matrix. And before we can talk about what a symmetric matrix is, we first need to address the idea of transpose. Transpose means that I'm going to swap the rows for the columns. So let's say that I have a matrix that looks like 2, 1, -1, 3, 0, 4, which currently is 2 rows by 3 columns. So it's 2 by 3. If I were to call that the matrix A, then there are 2 notations that our textbook gives for transpose. Sometimes there's a prime, doesn't mean we took the derivative. That A prime notation means the same thing as if we put a T up there. The truth is, I think this one's easier to type, so that's probably why we end up using this notation more in linear algebra. I think this one's a little more clear what's going on. That T is for transpose. So if I take the transpose of a matrix, my new matrix is going to become a 3 by 2, meaning 3 rows, 2 columns. And the way I'm going to get there is I'm going to take my first column and turn that into my first row. And my second column and turn that into my second row. And my third column and turn that into my third row. In general, taking the transpose of a matrix gives you some other matrix entirely. Their dimensions in general will not match unless it was a square matrix to begin with. So there's a special type of matrix where we call this a symmetric matrix. If A is equal to A transpose. Now, the only way that A can be equal to A transpose is if it's a square matrix, because in general, when we take the transpose, we're swapping the number of rows and number of columns. So unless they're equal, the numbers of rows and columns, there's no way this can be true. So we saw a couple of examples of symmetric matrices in lecture today. So let's see if we can come up with one ourselves. So first of all, we know that it needs to be square in order to be a symmetric matrix. And let's say I did something like 1, 2, 3, 2, 1, -4, 3, -4, 5. So this matrix B, if I find B transpose, so currently it's a 3 by 3. So B transpose will also be a 3 by 3. And I'm going to take my first column, and that will become my first row. 1, 2, 3. Then I'll take my second column, and that will become my second row. 2, 1, -4. And my third column will become my third row. 3, -4, 5. Looking at these two matrices, because every single entry matches, these are equal, which means B is symmetric.